Hello everyone. In this video, I'll show you how the neural network that we ran in the Arctic 7 FPGA can be expanded into a PhD level topic. I will also give a quick introduction to my research on convolutional neural networks. Before we start, one important note. This is the final video in the AI Accelerator series. In this series, we run a complete AI accelerator on the Arctic 7 FPGA to do real-time MNIST classification. Images are sent from the computer to the FPGA over UART. The FPGA receives the image, runs it through the neural network, and displays the classification result on the 7-segment displays. What you are seeing right now is the final end result. There are 6 earlier videos that walk you through building this system end to end. To find these videos, go to the channel, click on the advanced playlist, and scroll down to the AI video series. Alright, let's get started with how to take our feed-forward neural network project and turn it into something truly dissertation-worthy. In the feed-forward neural network that we built, we used this design to compute the dot product between the weights and input vectors, and then add the bias to form the neuron output. The main limitation is that we can only read one value at a time from the weights RAM and the input RAM. Because of that, the dot product computation takes many cycles, which makes the overall neuron calculation slower than what we'd like. So one key question remains, and that question is, how can we make the computation happen faster? The bottleneck in our feed-forward neural network isn't the math, it's memory bandwidth. Right now, we read one weight and one pixel at a time, so the dot product takes a lot of cycles. The speedup comes from packing memory so that each read gives us multiple values, like 9 at once, so we can do 9 max in parallel. The trade-off is that we must redesign the memory and address generators to produce 9 values per read. When you build an AI accelerator that runs fully on-chip on an FPGA, meaning no system on chip and no DDR, you're forced to store the inputs inside of block RAM. And block RAM is not something that we can redesign however we want. It's a fixed physical hardware block with fixed limits. You get a limited port width and only 2 ports. So the memory system has to be built around the block RAM and not the other way around. Therefore, to keep the design synthesizable and realistic, our memory architecture must be designed in a way that mirrors the physical limitations of the hard-coded block RAM cells. For example, on an Arctic 7 FPGA, this means that the data width of a memory unit can be no more than 9 bytes per port and have no more than 2 ports per memory unit. So, if we wanted to redesign the compute unit to run faster, we'd make a few key changes. First, instead of doing one multiply it and one accumulate over many cycles, we'd use a combinational multiply-accumulate block that can process multiple values in parallel. Second, we'd upgrade the memory system so that the weights RAM and input RAM output 9 bytes per address. With that wider read, we can pull multiple pixels and multiple weights at once and feed the MacBlock more data every cycle. With those changes in place, the exact computation runs at a much higher throughput, so each layer finishes much faster. So now it's time to discuss my PhD research on convolutional neural networks. This is not going to be a deep dive, but instead will be a high-level summary of how it works. My research is on how to do convolutions very efficiently. Convolutions are used in machine learning models and are needed for image processing. This is an extremely important space in research for both medical and military applications because it allows you to detect any object, whether it be a tumor or an enemy vehicle. These models are really useful because they can often outperform human beings at a fraction of the time. This is extremely important in mission-critical environments, such as in determining if a patient has a dangerous disease or in determining if there is an enemy present. Before I can explain how a convolution works, I need to quickly define what a tensor is, because tensors are what we use to represent both the inputs and outputs of a convolution. In this context, you can think of a tensor as multiple two-dimensional matrices stacked back to back. An RGB image is a perfect example. It has one matrix of numbers for the red channel, one for the green channel, and one for the blue channel. When you stack those three matrices along the z dimension, you get a three-dimensional grid of numbers. That's a tensor. Below, you can see the full RGB image tensor, and you can also see the individual matrix that makes up a red channel. The key idea is this. In convolutional neural networks, both images and filters are tensors, and the convolution is the operation that transforms one tensor into another. A convolution is a mathematical operation that takes in an input tensor, like an image, and a set of small tensors, called filters. Using those filters, it produces a new output tensor, which you can think of as a new image representation. And a convolutional neural network is just many convolutions chained together. The output of one convolution becomes the input to the next convolution, over and over, building up more and more useful features as you go. The great thing about convolutional neural networks is that in hardware, it all comes down to building a circuit that can do convolutions efficiently. Once you have a fast, efficient convolutional engine, you can chain it together to implement basically any convolutional neural network built from that kind of convolution. When you build a convolutional neural network accelerator, the bottleneck is almost always data movement, not the math. The compute itself is straightforward, but the hard part is getting the input tensor out of memory and into the compute pipeline fast enough to keep the hardware busy at every clock cycle. So the core of my research is in designing custom memory layouts and deterministic address generators that actually map well onto real FPGA block RAMs. In other words, instead of storing the input tensor the normal way, we store it in a way that makes streaming efficient. The goal is to pack the tensor with minimal wasted memory and stream it out in a predictable, orderly pattern, so the convolution engine can consume data continuously without stalling. The animation to the right shows how an input tensor would need to be streamed out of memory. So yeah, that's pretty much the kind of research that I'm specializing in for my PhD right now. If you want me to make videos on the convolutional accelerator, leave a comment and let me know, and I'll turn that into a series. Alright, that's all for this video. Be sure to like, comment, and subscribe, and I'll see you next time.